Good morning, good evening, good afternoon. And yes, I'm well aware that it's not Tuesday. I'm well aware that it switched. It's going to switch again. So we'll announce that when Brad Guy gets here. This is Science Tuesday on a Wednesday, but not staying on a Wednesday. Moving again. So, ladies and gentlemen, welcome. Brian S., aka Nucleatic Gaming, will be joining us in a little bit here. So we'll start it off, go through the book definitions, and then by that time, Brian should be here, and we should be good to go. So we're going to take a look over here at the rumbles first. We have the big giant fuck over there. I was only like 5 minutes. No, 8:36. I was only 4 minutes late and gay. We have Man Bun that dropped in and left a like. Much appreciated. We have big giant fuck over here. And I think I pinned my link already, so we're good there. We have Sleazy. What's up, buddy? Vroom vroom mother cluckers. Texting and driving is the OG daredevil shit. That it is. But be safe. We have all kinds of time. We have Tweety. Hello. We have me. More on time than you. But no, I wasn't. 4 minutes late.
Vagina.
That's my new clip. I love it. All right. So, ladies and gentlemen, we are going to continue our world of quantum mechanics and quantum physics. We're going to start going down the rabbit hole. Like I said, everything that you learned last week on Science Tuesday on a Wednesday, just forget all that. Because, yeah, it's not going to make sense. Welcome to the realm of quantum physics. So, you don't see a pin link? Oh, shit. There we go. Now I have it. All right. Oh, you said was on meaty time. Got it now. Got it. All right. So link's pinned. Like I said, Brian will be here at some point. So let's get into it. So we're on the uncertainty principle. The Heisenberg Uncertainty, I'm going to go to the book first. Principle is a statement about the way quantum objects such as atoms and the smaller particles inside atoms behave. So we get into like Higgs boson and things like that. It was developed in 1927 by Werner Heisenberg, and so it bears his name. The principle states that we can never know exactly where an electron, say, is located, while at the same time knowing exactly how fast it is moving. Either property, its speed or position, can be measured to an infinite accuracy in principle, provided we sacrifice any knowledge of the other. So, basically what that's saying is we can't do both. We have to pick one. Either property or speed or position can be measured to an infinite accuracy in principle. Oh, I read that already. There we go. This is not a shortcoming of our understanding of the workings of nature, nor is it due to the sheer minuteness of an electron, but it's simply the way electrons are. In fact, it has nothing really to do with us at all. The electron itself does not have a well-determined position and speed. The best we can do is to identify a region in which the electron is likely to be moving. Another way of stating the uncertainty principle is in terms of energy and time. We can measure the exact energy of a particle provided we do not care about when it has the energy. Conversely, if we fix the time measurement exactly, then we give up any hope of finding out how much energy it has. What's up, AP? And Sleazy Society? Where'd he come from? All right, so our related theories are atomic theory, which we went over 2 weeks ago, quantum mechanics, which we went over last week, and then some that we'll go over in the future are Schrodinger's cat and parallel worlds theory. According to the uncertainty principle, there's only so much you can learn by measuring subatomic particles. So our 3-second thrash idea, the harder you try to pin down a subatomic particle, the faster and more frantically it zips around and tries to escape. The 3-minute thought. The uncertainty principle is often mistakenly taken to mean that the instruments you use to probe the subatomic world are clumsy and inaccurate. In fact, it is really a very powerful statement about the way nature behaves at these tiny scales, and it has many important consequences. For instance, without it, the sun would not shine, since it is the reason hydrogen nuclei are able to fuse together to produce light and heat. So, just like the previous, this is critical for our world in so many ways. And it leads into next week. Hell, we might even do it this week if Brian's up to it, but Schrodinger's cat, that kind of thing. I tried to do Schrodinger's cat as an experiment, and my wife said, no, can't use the cat. Tried to explain to her that it would be both alive and dead at the same time, but that didn't work. Hey, Barbara. Okay. So we're going to start with a short video. Damn, this one was long. I really like this guy, but maybe we won't. Oh, Quidditch medals. All right. That's what I'm saying, D's. That's what I'm saying. Yeah, shit, because we're kind of just killing time till Brian gets here anyways. A normal person would have moved it back to, a different time, but I'm not normal. Yeah. It's okay. Like I said, this is going to be moving around again. So we'll watch a little bit of this video. I'll stop and transform the content and, all that good stuff. Take this for a moment. Please remember, hit that like and subscribe. It would be much appreciated. Wow. Sorry, I just got a glimpse of the markets dropping fast and all red. That's cute. Anyways, different Brian must be taking full advantage of. I don't know what that means. We could do it with a spider. That's a great idea, Dazzer. That's a great idea. We could certainly do it with the spider. Or maybe like an ant or something like that. Yeah, me too, AP. But I think you got to crack a couple eggs to make an omelet. And our eggs are about to get really cracked really hard. That wasn't a euphemism. So, sorry, I'm oh, I know what you're talking about. Okay. Yeah. Yeah. Undoubtedly. Brian's I mean, he shows up when he wants to. That's kind of his MO. It's deep ingrained in his culture. I disagree. All right, so we'll watch this guy explain it and then go into more detail.
Heisenberg's uncertainty principle.
Hey, Jenny,
And
I was
I'm gonna
around.
start with the equation.
We had to record a video because we were well, shit, I guess I can say it. I'm gonna be gone this weekend for the holiday. It looks like Friday's gonna get. It looks like Friday may get nuked. And Saturday we already did the C5 mission. So that will play as a premiere. Sunday, I'm going to try really hard to stream because it's my lover and friend Brian's birthday. Stream with him or stream independently or take all his views away. One of the, something like that. We'll see what happens. And then I'll be back by Monday. So that's kind of the plan. I'll put together a video. I have one more pre-record that will go out at some point. Might be Friday, might be Sunday. But at some point. So we drug Dazzer in with us. Hey, Rose. How are you? Good to see you. Yeah, we drug Dazzer in with us. Okay, so we'll get to this video. I don't know how far up Brian is, but his time, his world, we're just living in it.
Delta x times delta p is equal to or greater than h divided by 4p. So what exactly does this mean? When you think of x, what do you think of? X is basically the position of something on the x-axis. So delta x is the uncertainty in the particle's position. Delta p is the uncertainty in the particle's momentum. Now, the momentum of an object is the product of the mass and the velocity of that object. H is Planck's constant. So what's the basic idea behind Heisenberg's uncertainty principle? The basic idea is this. The more you know about the particle's position, the less you know about its momentum. And the more you know about the momentum of a particle, the less you know about its position. Now, you need to know that we're not dealing with a single value. It's hard to know exactly the position of an electron, but rather, we're dealing with a range of values.
So this
Now,
gets into those clouds that we talked about last week. So it's going to be we can predict that it's going to be in one of those specific areas. In that electron cloud somewhere. We don't know where, can't pinpoint it. But the closer we can get to pinpointing its position, the less we learn about its momentum. And if we want to see how fast it's going or how quickly it's moving, we lose sight of that position in the electron cloud. And again, this isn't, as the book stated, this isn't something that we just can't measure it. It's just the nature of quantum physics.
Planck's constant is a very small number. It's 6.626 times 10 to the minus 34. So what this tells us is that Heisenberg's uncertainty principle applies for things that are very small. Things like an electron or a photon. Those are things that are very small. It doesn't apply for things that are very large, like a soccer ball or a car.
Hang on. I'll put that number in. This is that number actually written out. That's how small of a number we're talking. We're not talking much at all. So Twitch really hates me. It won't even let me post comments anymore. So a lot of zeros. So we're talking about just incredibly small numbers.
It's not significant for those things. So let's see if I can illustrate this concept. Let's use a real life example. Let's say if I have a ball on top of a cliff and I kick the ball towards the right with a speed of 15 meters per second. If I know the speed of the ball and its direction, and let's ignore air resistance and any wind effects. Let's say the ball is only under the influence of gravity. I can predict with good certainty where exactly this ball is going to land using the concepts of projectile motion. And so whenever you're dealing with large things, large objects, the behavior of large stuff is relatively predictable. The behavior of small things is less predictable. There's more uncertainty with small things, but there's more certainty with large things.
That's a true statement if I've ever heard it. But no, for real. So if we're... Yes, I do. Have one. Anyways, so we can predict with a high degree of relative certainty where that ball is going to be. So we'll be able to calculate and even plot out the different points at different times. So we could do an entire graph and show the entire progression of that ball going through space and time. And even realistically, with enough information, could calculate the bounce and the, all that kind of things. We can't do that with super small objects. So this is what drove Einstein nuts, because he's trying to find a causal link for his grand unification theory, and it's so different, so foreign once you get down to the scales that we're talking about. And it's not, there's different fundamental forces and different different attractions, different repulsive behavior. Explain it in Joe Biden terms. Well, you see, if Corn Pop was throwing that chain at my car and it hit a box of documents, we could tell which document it hit and what year I stole it from Barack Obama. But when we're talking about these little things, it's like that ice cream. I just don't know where it went. I didn't eat it all. I couldn't eat that much ice cream. Was that good, Jace? I'm clipping that, by the way.
So let's say if I had an electron and I shot it horizontally from the top of a cliff. Now, it's hard to predict the behavior of an electron. It might go straight, it might curve this way, it might curve that way. So I can't say with exact certainty that the electron is going to be right there. Rather, I can increase my certainty by saying it's going to be somewhere between these 2 points. So I can't give an exact point, but I can say it's going to be somewhere between those 2 points. So I need to speak with a range of values rather than one single value. And so whenever you're dealing with small things, you need to talk about probability rather than exact values. A good example to illustrate this.
And so probability, this section of probability, that doesn't rule out that it's over here, like way up in this top right corner. It also doesn't rule out that it's here, because it's just there's a probability that it is in this general vicinity of area. There's little blocks. So even when we apply uncertainty and Heisenberg's, we still don't have a concrete answer of where that particle is. We have a pretty good idea. We have a pretty reasonable guess, but that's as far as we can go. We can go to a guess. So
Is the toss of a coin. Now, if I toss the coin once, I can't tell with exact certainty if it's going to be heads or tails. It's completely random. However, if I toss the coin 100 times, I could say that it's going to be somewhere between 40 to 60 times that I'm going to get heads, because the probability is 0.5. So it's most likely to be around 50, but I can't say with exact certainty that it's going to be 50. So I can't give a single exact value. If I say it's going to be 50, my certainty will not be that great. It's a small chance it's going to be 50. However, if I speak in terms of a range of values, like 40 to 60, I could say I'm 95% confident that it's going to be between 40 to 60. But I might be only maybe 5% confident that it's 50. So with events that you don't have control over, events that are random, it's hard to predict the exact value of what that event will be. However, you can increase your certainty if you speak of it in terms of a range of values. So let's say if instead of tossing a coin 100 times,
right, and then we get into distribution plots, and we get into shit. I forgot what it's called. Somebody help me. What is the? I can't remember what it's called, but Brian will know. But we can include more and more the more we branch out, and the more that we include. Obviously, if but as we get more specific, we're not going to get as close. But this reminds me, of a case where a guy got shot through the head and torso because he was laying down, but on the other side of the wall, the gun went off. Huh. Guy got shot through the head and torso because he was laying down. Oh. Oh, thanks, AP. I'm not even watching Ozzy right now. Yeah, I was just trying to think about that, how that happened, but huh. But yeah, so you get more certain as you expand. So if stalling over, what's up, buddy?
Hello, everyone. Rule number 4 at my work: don't jinx it. So you can thank my wife for saying I hope red lights. God,
You weren't that much later.
I hit every single red light. It was so bad.
I mean, it happens to the best of us.
That's true. So where were you at? I missed like the last minute and a half.
The last minute and a half, I was trying to think of what the hell. I don't even know how to explain it. So standard deviation. Thank you. You said it, or just your presence brought it back to me.
Okay.
Said my black man has now entered the chat. We're talking about
what about standard deviation?
So I was thinking standard deviations of how much the quantum hurts your brain. It really does.
See, I thought you shouldn't try to apply standard deviations to any kind of Heisenberg uncertainty because it can just straight up be anywhere. It's not going to like bell curve itself.
Well, I'm just trying to explain it in terms that people might pick up on. I understand that you're not, because it literally could be anywhere. But I was explaining standard deviations. If we include more of the picture, we're going to get more of the result. So there's more of a chance. So let's say you get a prize if you find the gold golf ball. Well, there are 10 buckets that could have the gold golf ball. So if we include one bucket, if you can only go look through one bucket to find the gold golf ball, there's a very low probability that you're going to find it. You could, but low probability. If you do 5 buckets, there's more of a chance. If you do all 10 buckets, generally you would think, well, shit, I won. Like, it's there. No, it's not. It doesn't have to be. Could be. But you don't have the traditional method that you would if the golf ball was in any of those buckets. Does that make sense, Bry? I mean, the golf ball could be in Brian's pocket in Australia, and we're doing the golf ball thing in Detroit, Michigan, and it's in one of the 10 buckets, supposedly. Ooh. Totally a mistake. Sorry.
See, just like me, I could be in the stream or not in the stream.
Exactly. So he could have. So we don't know Brian's position, correct? We didn't know Brian's position that whole time, or we did. We didn't. We don't know Brian's position, But shit, I just lost.
Well,
how
you
to
know
explain that.
exactly where I am now, but how fast am I moving?
Right. You know where he is, but yeah. Do you know that he's not still driving? We know what his position is. But if we're making him an atom and doing superposition, then we have no idea. What's up, Jacob? No worries, buddy. We have zero idea. Like, we have a probability, and that's what I'm trying to get at, is we have a probability of where he's at, but we don't know that he's there for sure. Like, even if we knew excuse me, even if we knew where his house is, we
You
still
don't know which
that
apartment
he's
I
there.
am.
Right. Even if we knew the apartment, we still don't. That's a great one. So we know the state, right?
Should. Chicago's a
Joe-
shithole.
It's like Joe Biden. You don't know where his brain are or who he's going to lick next. Exactly. But so the more information that Brian gives us, the more certain we can be of his location. But we never actually asked him if he was at his house. So he could give us all the way to the apartment number, and we'd be reasonably certain that he's there. But we don't know that he's there because we never asked him. Right? Is that a better way?
That's significantly better than the weird golf ball thing.
God damn it. Okay. Well, I was trying to work it out. So the more information we gain, the more we can nail it down. But even though we have all the information, we don't know that he's there. And at some point he was, and at some point he probably will be. So that takes in the time aspect or the momentum aspect, because he will be there at some point. But is he there right now is the question that we can't answer because we don't know. I said something wrong. What's the problem? Or you're not paying attention? Exactly.
No, I'm trying to think of a better analogy.
Nope, that was the best one. We're moving
Absolutely,
on.
100%.
Now, I can't say with exact certainty that 516 times it's going to be heads, because you don't know with that degree of certainty. However, I can say that I'm going to get heads somewhere between 450 and 550 times. So if I flip...
So, are you
God
a man
damn
who's
ads.
looking to
I didn't
overcome
download this video.
pornography addiction or anything
Yo,
under the
smash
umbrella
your
of
pass.
Pornography
addiction,
addiction.
anything,
Smash.
right? Maybe only
flip the coin 1,000 times, it's going to show up as heads somewhere between these two values. And I can be almost 99% confident that it's going to be in this range.
Can we,
this
though?
is the basic idea behind the law of large numbers. When you're dealing with small things, there's too much unpredictability, too much
There we
uncertainty
go.
with small things. Like if you flip a coin,
This is the part where he's getting to. We can't do that.
However, if you flip it 1,000 times, you can predict with a lot of certainty a range of values in which it's going to be at. The probability of getting heads is 50%. So it's most likely to be at 500 than at 550. But you can't tell if it's going to be exactly 500. So if you speak of it in terms of a range of values, it becomes more predictable. And that's the basic idea behind the law of large numbers. Large events are more predictable than small events. Now let's go back to this equation.
I don't know how much I like
we
that
said
one
that
either.
the more we know about the position,
I
of
prefer
the
looking at it
particle,
like a
less we
deck of
know
cards,
about its momentum.
personally.
So let's draw a
Well,
number
you
line
explain then.
to illustrate the position.
Deck
Well-
of cards, go.
So, to me, how I think about it is pick a card, any card, and then you start picking cards out of the deck, and there's a higher chance of it being the card that you're asking for, depending on how many cards you pick up out of the deck. But there's still a
Okay.
chance that it's not that. And also, the Joker's not in 52 cards. So there's also a chance 52 cards. there's a chance it could be the Joker also, which would be the 53rd or the 54th card in that deck of cards. Thus, you have a chance of not having your card in there at all because it decides to do something stupid. Such as an electron can just do something stupid. So you have a really high chance of knowing where it is, but it could straight up not be. And that probability of it being the 53rd or the 54th card would be the uncertainty principle at its best.
Okay. So let me just a second. I have a deck of cards. Pick a card.
The Jack of Spades.
Of course you would.
And now throw them on the floor and let's play 52 card pickup.
Hell yeah. Okay. So
Don't worry about it, Isabel.
hang on, I'm working on it. Oh,
V-cam, you fucked it up. You boomered it.
okay. So gotta call a spade a spade. So we have all the cards. So now we have, so the chance of this being a card, the card that he picked, was very low. The chance that it's still in here is what, 99%? So we go to the next one. Okay. So now you're shifting value. So as we move, there's more of a likelihood that it's left in this deck, the more it doesn't show up here. So if we keep going, going, and going, and going, and going, and going. Yeah, I'm going to go through all of them.
But this is just how probability works. Every time he pulls a card, there's a higher chance of it being the card that he's looking for. Unless he puts back, which that's not what we're doing here.
Yeah, we're not gonna do that. So we're continuing. Oh,
Jack of clubs. I said spades.
I know. There's a method to my madness. Hang on. So what the card is it's highly likely that it's still in here, right?
Oh, extremely highly.
Extremely highly. And we get higher as we go. So Queen of Spades or clubs. Now we're getting to holy shit, it's gotta be in here, right? Like, okay, so it's still probably in here. It's in here. It's in here. It's in here.
Oh my god.
Okay, so we are reasonably certain that is. I want to play euchre too. We're reasonably certain that it's over here because it's not over here, right?
Correct. What are the fucking odds?
What are the odds?
Really damn low.
So our certainty is 99% that it's here, right?
Unless it's the Joker for some ungodly reason, and then it's not in the deck. But
It's 99%, right? That it's here?
should be.
Nope. Because that's just how it fucking works. It's way over here.
We got jokered.
So it doesn't have to be in this deck of cards. It could be way over there. it could have been the last card. So if we pick it, I won't fuck with it this time. So pick a different card.
Fuck, I don't know. Queen of Hearts.
Queen of Hearts. Okay. Just playing it straight. So we're getting more certainty that it's over here because we haven't found it yet, right? I didn't do anything this time, so I'm gonna fucking... And this is 52 cards
soon.
this time.
It should be soon.
So we're damn near half. So now it's half that it could be over here, half that it could be over there. There's your Jack of Spades. Shut up.
God damn it. What'd you do?
I didn't. I swear to God it's in here this time. So now we're better that it's over here than we are that it's over here. Somebody could count. And there
Got
it
it.
is.
Thank God.
So that's where it was this time. So, I mean, that's kind of the illustration, is it could literally be anywhere in this deck of cards or not in this deck of cards, but it's got to be someplace, but we don't always know. 9 more cards. You were wrong, D's. Okay, so we'll do a third time because third time's the charm. D's, pick a card. JSDs. Pick a card. Not that King of Spades. Hit.
Ace of Clubs.
Well, house one. Or the player one. Ace of clubs, you said?
Yep.
Okay. So again, it could be literally anywhere. So
So I'm also eating dinner.
yeah, I just finished.
Spicy chicken nuggets.
So again, when we're taking and this is a perfect explanation. Thank you, bro. Because at some point we should see it, the first card, or one of these first card, one of these first third of the deck, but we haven't yet. But it could have been. It could have been the first card that we flipped.
Well, we're not that lucky.
So now we're 2/3 of the way through the deck. Thereabouts. And we still haven't found it. So, Ace of Hearts. Ace of Spades. Like, again, we're running out of cards. And there it is. With 6 cards left. So it's the 48th card. These are from the D Las Vegas AP. So, I mean, we literally, so let's say I'm going to cheat. So let's say our card is Queen of Diamonds. Oh, look at that. It was the first card. And that's kind of the illustration. So then the Queen of Diamonds could be... Shit, I just put it in there and I don't remember where I put it. So it's the same thing. Okay, so now we add random chance to it. So Queen of Diamonds. So this isn't just a deck anymore. So now we're adding influence. So
We're looking at an electron cloud. Ooh.
Yes. we are.
Look at all these random positions it could be in. We're
Very
not really
well could
sure
be.
where it's at. We can find it though.
We can find it, but it will
I've-
take time.
It takes time. It takes a lot of guessing, but we're still not. Then we're not 100% sure about a lot of other things too. After we find it, it causes uncertainty in other variables also.
There it is. It was right there. But it's not likely to be there again. No, I'm just saying, AP, that's what these cards are, Vegas. So yeah, that's an electron cloud, and these are all the positions it could be. But it also could be way over here, or it could be way over here, or on my head, or in Brian's butt.
Maybe. There's a lot of stuff already in there, so it'd be kind of hard to find.
I'd go looking though. Shut up. And of course it would be easier if we did it this way. There's the Queen of Diamonds. But that's not what quantum mechanics is. And that's kind of the so this is the quantum realm where we can't see shit. And this is our realm or our world. We can see where this queen's gonna be. Because we can just look through and we don't have to independently verify every single time. Like we can very easily find that queen. And this is our world. This is the quantum world. We don't know where it's at.
Yeah, and it's so small we cannot find various discrepancies between individual particles and whatnot and fractions of particles. So
Right.
there's like we can't see an electron like by itself. So there's no reason to like even describe it in a terms of where it exactly is because we can't even really see it anyway. So this analogy kind of falls apart a little bit just because of that. But it does give you the kind of idea. Okay, we don't know where it is. We have a good guess. It is somewhere in this deck of cards, and that's about it.
Maybe.
We can't sift through all of them like we can sift through a deck of cards.
Right. So it's almost like 4D. Well, it adds the fourth dimension. That fourth dimension is time, and that time is the delta P. So yes, it is 4D. Correct. Right.
Momentum is speed plus mass. So yes, it adds it adds speed. It adds inverse time.
Well, yeah, but it's still time.
Yes. It adds inverse time. Yes.
Like I said, I'm trying to explain it in like common words, not be a scientist.
It adds time.
Thank you, dear. Oh shit! And I just knocked over a bunch of shit. All right. So continuing on, friction. There's not really friction in the quantum realm as we would know it. See, and that's what I was talking about. The fundamental forces are different because we don't have, we don't think we have gravitational interaction, or we're not having these nice clean orbitals. So, yeah.
Magnetic forces are the closest thing you're probably going to get to friction.
Well,
and even then.
strong and weak nuclear forces, magnetic forces. What are the other quantum forces? I forgot.
Oh shit. Gravitational forces, I believe, are actually quantum.
But
They're
it's
just
not.
so incredibly small.
It's not traditional gravity though. It's quantum gravity.
That's a good question.
Strong. I forget. Or I think there's 7. Strong, weak, magnetism. I take it you're looking it up.
I'm trying my best.
Okay.
It's not easy. It's just some like underground shit.
Yeah.
It's gravity, electromagnetism, weak interaction, strong interaction is 4.
Okay. I thought it was 7, but shit, we were better than we thought. Strong, weak, gravity, magnetism, electromagnetism.
Well, there's also Higgs,
liquid.
but we don't talk about Higgs.
Nope. We're not talking about Higgs.
We don't talk about Bruno.
Jesus Christ, the Higgs. No, we're not going to talk about.
We're not going over Higgs.
We're not going over Higgs. We're
Fuck
not
Higgs.
talking about. We're not talking about CERN at all. Even
So
remotely.
are there 7? Probably, but there's 4 of them that are actually useful.
Oh, so I was right again.
Well, Higgs is one of the 7. You want to do Higgs? We can do Higgs.
No, I didn't say we were doing Higgs. I just said there are 7.
There's probably other ones that are missing that I know of, but I can't pull out of my ass.
Yeah, I'm not even going to try because that's going to take us down the track of where we don't want to go. Anyways,
Exactly.
continuing.
Position of the particle on the x-axis. And let's say that the particle is most likely to be at the center of this number line. Now, we can't say with exact certainty that it's going to be at position 0 or position 0.5 or position. What is the uncertainty in the position of an electron given an uncertainty value of 0.15 meters per second and the velocity of the electron? So our goal is to find delta x.
Oh, we're doing math.
That's what we're looking for. And we're given
Oh, God.
delta v. It's 0.15 meters per second. And keep in mind, the mass of an electron is 9.11 times 10
Fuck is this, Khan Academy?
minus 31 kilograms. So according to Heisenberg's uncertainty principle, delta x times delta p is equal to h over 4 pi. So our goal is to find delta x. So we need to
Fuck you, I like h bar over 2 better.
1 over delta p in order to isolate delta x. So these two will cancel.
Less math.
And so delta x is h over 4 pi times delta p. Now, delta p, we know that momentum is the change in mass times velocity. Well, momentum is mass times velocity, so the change in momentum is the change in the product of the mass times the velocity. Now, the mass of an electron is pretty much fixed. So this is going to be m and delta v for this particular problem. Now, there's one little thing I need to add because this is supposed to be an inequality sign. So delta x has to be equal to or greater than h over 4 pi times delta p.
You already fucked up.
So let's go ahead and calculate that value. So Planck's constant, we know it's 6.626 times 10 to the negative 34 divided by 4 pi. And then we have the mass of the electron, which is this number, multiplied by the uncertainty in the velocity of the electron, which is 0.15. So go ahead and plug this in. See what answer you get.
No.
Fuck me. No, I'm
refuse.
not. I'm. Okay, I'm gonna do it real quick. It's 7.
Make your life just so much easier and just do 6.626 times 10 to the negative fucking hell, negative third, and then change it to 9.11. Make your life easier. Just get rid of some of the fucking times 10s. AP. Some pies are better than others. Oh, you're damn right. I cannot believe this guy's literally plugging this shit in.
It might not.
Now watch, he's gonna go to like the different amount of decimals than you because you fucked up your significant figures, you fuck.
I exactly know. I know that's gonna happen. I know that's gonna, because I'm just doing 3.1459. I could just do pi. I mean,
Fuck you and your significant figures proceeds to only round to 2 decimal places of pi, 3.14.
so I'm using
Hold on, let me grab a circle. This is 4 pi. No.
I don't exactly know how to use this goddamn calculator either. I'm just using the computer one, and it's
Dude lost his TI-82.
no. I don't want to have to fucking go grab it. Yeah, fuck it. If I had my calculator, it'd be different. But
So the uncertainty in a particle's position is 3.86 times 10 to the negative 4 meters.
oh,
So if you convert that to micrometers, if you divide it by 10 to the 6, or rather 10 to the negative 6, I'm just going to write the answer here. The uncertainty is 386 micrometers if you round it. So let's say this answer. So that's the uncertainty in the position of the electron. Part B, let's calculate the uncertainty.
Hold up, I already found a fucking error. This guy's a numbnuts.
yeah,
It's not an equal sign. You did it again, loser. Shoot.
right,
2 kilogram ball.
It's that or greater than.
right. So it could be okay.
Now let's use the same equation. By the way, this should be equal to or greater than.
Thank you.
I keep forgetting that. This is going to be h over 4 pi
Whoops.
m delta v.
Fucking idiot.
So
Corrected
the
in
only thing
real
that's
time.
changing
Bitch.
in part B relative to part A is the mass of the ball. It's 2 kilograms instead of this tiny mass. And so the change in velocity is still going to be 0.15. So now let's see what's going to happen. So what I got is 1.76 times 10 to the minus 34 meters. Now, in terms of micrometers, if we divide that by 10 to the negative 6, it's still going to be very small. It's 1.76 times 10 to the negative 28 micrometers. So let's compare these two values. What do you notice? Which of these values is measurable? We can measure 386 micrometers, but we can't measure this tiny number. It's so insignificant. And because the mass of the ball is relatively large compared to the mass of an electron, the uncertainty in the position of the ball is extremely, extremely tiny. It's so tiny that it's not noticeable. We can't measure it. So therefore, we know exactly what the position of the ball is going to be. We're not uncertain about where it's located. But
Right.
we can't be sure about the position of the electron because it's so tiny.
Yes.
The size of an electron is a lot smaller than a micrometer. So within 386
Sometimes you need that
micrometers,
piece of
that's
paper,
a lot
though.
of space for a tiny particle such as an electron. So as you can see, there is a huge uncertainty in the position of the electron given this small value in the velocity of the electron.
This isn't fair though, because we're talking about an electron in a 2 kilogram ball. So when you're talking about range of that, like proportional range, I don't.
Okay, fine. Do the proportional range between an electron and a neutron. It's still massive.
Well, I know, but I'm talking about proportional range between a 2-kilogram ball and an electron,
Yes.
right? 99.999% of teachers suck. I would say like 95% of teachers suck.
I've had some good teachers. One of them taught me how to knife fight.
The more you know with your black teachers.
He was white.
Of course he was.
He handed me a freaking training knife that the military would use, like the plastic ones, plasticky rubber ones, and he's like, "All right, kids, go stab each other."
That's awesome.
This was military history.
Whether you're gonna live or die. If somebody stabs you in the chest, there's an uncertainty that you actually die. Right?
I guess.
I agree. I missed all of chat because
I missed a lot of chat because this video, we're trying to find his freaking problems in his math. Something about a rogue black hole. Well, my black hole's pretty rogue. Anywho.
Okay, let's not pick apart this guy because we can fuck up too. So
That's true. That's true. I fuck up all the time.
yeah, me too.
But no, he's done nothing wrong in this one so far. It's kind of like one of those, like those weird squishy balls that you get from the carnival where like you squeeze one side and all the goo goes to the other.
Yes.
That's kind of like this, where the more uncertain or the more one side grows, the other side shrinks, the uncertainty. So like the more the mass grows, the more the more you you reduce the size of the uncertainty type of thing. You got to squeeze all uncertainty out of it to the other side.
Yep.
The other delta.
Absolutely.
One's big, the other one's small. If one of them's really small, oh man, you're screwed.
It could be anywhere.
It could be anywhere. It could be in my socks.
So to go back to the card analogy, it could be like if we're talking about the 2-kilogram ball, it's in that deck somewhere, and it's probably in the first 10 cards. If we're talking about probably even less than that, probably the first 3 cards, maybe.
No, we just know that it's in the cards. But as we have less cards in our hand, we're less certain it's there.
That's true. Okay.
Say we have all 52 cards, we know it's in there. But if we discard 10 of them without looking at it, we have we have a less certain chance of it being in the cards we have in our hand if we get rid of like 50.
All right. We got like 2 minutes left of this video.
Now, granted, the uncertainty value in the velocity of the electron is relatively small compared to the practical speeds of an electron, which can easily be hundreds of thousands or even a million meters per second. And so 0.15 is very small compared to such a large number. And so that's why the uncertainty in the position of the electron is so huge compared to the size of the electron. So I just want to point that out. But the purpose
We're
of
getting
this
into
talk
spin
is
next,
to help you
Jacob.
to see that
That would be next.
large
2 weeks.
objects, large things are more predictable than small things. So as we increase the mass of the object, the uncertainty in the position of the object decreases. So for something as big as a ball, we know exactly where it's located. We know its position. We're not uncertain about that. But for tiny things like an electron, well, there's going to be more
Or
uncertainty.
Brian's penis.
We're not sure exactly where the electron is going to be at. We don't know its position.
No.
Exactly.
No,
because it's
my
tiny and
penis
it's
is a
almost
very
infinite.
large weight. We know exactly where it is, and
So
it's
that's
inside
the
Meaty's
motive for
mom.
this video. Large things have behaviors that are predictable. there's not much uncertainty with large stuff. The small things, there's a lot of uncertainty with it. There's a lot of randomness. You can't predict the behavior of small stuff like electrons and
Like a Napoleon complex.
other stuff like that.
Exactly.
So that's it for this video. Thanks for watching and have a good day.
You too, buddy.
I like this
You
guy.
too. He's
I like
not
to give him
bad.
crap, but he's a good guy. He actually is pretty good. He's pretty good at that.
No, I agree. So, I mean, there's not a shit ton more to Heisenberg's principle. So the question is, do we go into Schrodinger or do we save that for next week?
Schrodinger kind of leads, the mathematics of it kind of leads into it. It kind of becomes useful.
Okay, so here's how, because the book people are probably smarter than me, I would hope. Probably not. I take that back. So next we have Schrodinger. And then after Schrodinger, we have quantum field theory. And then after that, we have quantum entanglement. So that's kind of the way I was going. And then unification. So that's kind of where I was going with it, is following the design of the book that I'm using.
Part of it will go right into it. The other part of it's just math that's really, really, really long. But it's all about energy. So we might.
Schrodinger. I think we should save Schrodinger for the end.
We might want to wait on Schrodinger.
So next we should go quantum field. And then after quantum field, we should go entanglement and then Schrodinger. Right?
Yes, probably. Quantum field is more of a wordy thing, so we should be able to make more word salad from it.
Brian's going to toss our salad next week.
Gross.
So yeah, I think
I'm not great with quantum field theory.
okay.
That one we didn't have to go over too much. Thank
As
God.
As we progress more into the physics side of it, then I know more of it than the chemistry side of it.
Yeah.
And Heisenberg's still on the chemistry side of it because you're trying to figure out where, stuff is for blah, blah, blah.
Definitely. Heisenberg is like the bread and butter for knowing electron clouds and whatnot.
Right. So that's Bry's side. And then the other side gets more towards me and my area. So yeah, I think it's probably, I know you will, Jacob. You're awesome, dude. I think it's probably best that we cut it off just because I think too much of this can just lose everybody and hurt brains. Sure does mine. I know that for sure. But yeah. So what do we... I'll let you griff first while I get my thoughts together.
Sure. Check me out on rumble.com/nucleatic gaming. All my stuff gets posted on Meaty's Discord. So if you get on to just click the link, you can find it there. But today I ended up playing Getting Over with Bennett Foddy and slowly descending into madness because that game is frustrating. I eventually start talking about a fish. I don't have a fish, but I kind of want one now after playing that game and realizing that I want a fish. God, I hated that game because it's meant to be frustrating. It's like Quap, except worse. Because at least with Quap, you could put like a rhythm in your hands. Oh, it's that game where you could just run like a track guy for some reason and put one foot in front of the. It's dumb. Anywho, yeah, this game's just frustrating. So I'm just gonna keep filling in random crap until Diablo comes out, and then I'm also gonna be streaming on Sunday because Birthmas, and it'll be fun. I don't know what I'm gonna be doing or playing, but I'll play something. Probably Skyrim. Might be a cannibal. So yeah.
Idea. And I'm definitely gonna drop it on Sunday at some point. Don't know when, but I will. So go over and check them out. Drop your own damn link because I don't know what Landers is.
I'll do it. I got it.
So go over on his channel on Sunday. I will be gone for the weekend. I will do a premiere of Sea of Thieves on Saturday. We've already recorded it. It's already processed. It's already ready to go. Friday, there's a high degree of likelihood that we're going to scrap Friday altogether. Just because of the way it's going to work out. And let's see. Saturday, Sunday. Sunday's Friday. Monday, I will be back. So we'll be good there. Yeah. And that's kind of where we're at. So, and then as of next week, we're going to change some things around. I think the current plan is we put up a poll, but I think we can give you the top 2 results. So the plan as of now, and we're going to work it out and kind of discuss it a little bit more. We are going to move science to midday on Saturday, sometime in the mid-afternoon. And then we're going to send you over to Brian's to play some kind of game. And I may join him if I get the invite. We'll see if he wants me to come play with him.
It'll probably be some kind of multiplayer game that should just be full of shenanigans, but different level of shenanigans than what you would get out of Sea of Thieves or something.
Yeah, so we'll kind of play it by ear, see what happens. But that's kind of the plan moving forward. And then Sundays may also move to kind of a more beneficial time so everybody can check it out. So
Smash Bros. I think there might be a multiplayer PC Smash Bros. Port that works really, really poorly and might be hilarious.
Then yes. So yeah, that's kind of the plan moving forward. As always, we really appreciate you stopping by and working with us as we kind of nail down the schedules. And I really like working with my friends, so it's cool. I think that's about it, right?
I think so.
All right. Once again, since I still haven't put it in the description, at some point I will. Thank you, Brian, for the outro music. It is fantastic and much appreciated. This is not it. This is funny. And then we'll go to the outro music.
Vagina.
Yep, I made that too, guys. Definitely 100%
No,
did
I
that.
made that one. I made that one.
Vagina.
God damn.
So now the outro is coming up that Brian made. So thanks for stopping by. Tomorrow I'll still be here. We'll do news and then movie night. Somebody tell me what one. Shit. Give me a second. I'll look.
Hellboy 1.
No, it didn't. I didn't even think it was up. Was it?
No, it was not.
Fuck. It's voting's already done. I don't know. There'll be a movie tomorrow. It'll be fun. So cool. Movie over on Discord. So thank you all. Everybody have a great night. And we'll see you soon. Take care.